Okay, so hopefully I've pulled a title out here that will draw a bit of a crowd and get some interest. In contrast to our previous presentation, who was talking about the implementation and the whole system cost, this is a focus on the processing costs associated with FOGO, which obviously there is a huge trend. We've all heard a huge trend towards introducing FOGO collection services and processing this material. And before any council embarks on such an exercise, they need to know how much it's going to cost and put it in their report and get approval from their councillors. So we hope this is a useful step in that direction. In the past, I have always used a rough rule of thumb that it costs about $100 to make a quality recycled organics product from clean, non-putrescible material like garden organics or manures, even when you have a relatively low cost of land and overheads. That's generally not borne entirely by the gate fee that's paid by councils. Usually there's some also achieve some value in the product made, and the split's normally 60-40 or 70-30 depending on the situation and the markets. But what we wanted to do was get much more accurate than that very general rule of thumb. So we consulted equipment suppliers and operators to understand a more detailed assessment of the full costs of building and operating a facility. And we'll get into the details now. So we looked at a limited range of composting systems that would be capable of dealing with the FOGO material that would typically be collected at a curbside collection service. We looked at all operational and capital costs, but the analysis excluded administrative overheads, product marketing and profit, and you have to consider all those things, particularly if you are, well, in all cases, basically, someone is inevitably taking a risk in providing this service, whether it's done in-house or whether it's delivered by a private sector contractor. So if they're taking a risk, it's a business, they need to get some reward for the risk they're taking, or at least partially cover that risk. Cost of land, in many cases, the local government is able to provide land. They're able to provide part of a finished closed landfill site or some other council-owned land that is appropriately, has appropriate DA, appropriate planning approval, and can be relatively easily licensed. Trying to get a planning approval and a license for a brand new site for composting, as many of you here would know, is quite an exercise. So it's much easier to work off an existing site. And normally those sites have, at least to the site boundary, a connection of power and water, so we excluded them from the analysis. We looked at 3 different scales, and we looked at 3 different covered or enclosed, in inverted commas, composting systems, and we looked at windrow composting as a benchmark, because windrow composting is the most common approach to composting in New South Wales and Australia still. Okay. So this focus is on centralised composting facilities here. We're not talking about home worm farms or home composters or even small commercial units. We're talking about above 5,000 tonnes. So small regional facilities like Taree or Kempsey potentially could aggregate 5,000 to 10,000 tonnes per year. Large regional centres like Orange or Dubbo could aggregate around 15,000 tonnes a year. And if you're in a large urban centre like, for instance, Newcastle or Lake Macquarie, 30,000 tonnes per year or more is feasible to get into one location. Less than 5,000 tonnes per year is usually not attempted, even for windrow systems. They do exist, but they're rare and they're not very commercial. They're not very profitable, generally speaking. Again, traditionally, the thought has been that building facilities less than 20,000 tonnes per annum for FOGO is basically an expensive option. Because the capital costs, there's a minimum capital cost you've got to spend, and if you just don't have enough material to amortise that across. But we included 15,000 and 5,000 because it's actually quite difficult to aggregate more than that amount of material in some regional areas. Okay, so the systems we modelled in more detail: open windrow with self-propelled turner. And I'm going to move through these fairly quickly. If you have any questions about the detail, happy to answer them at the end or afterwards. Aerated static pile with a pipe on ground and a compost cover. For those of you who watched the presentation this morning, the Recology site that San Francisco sends their material to uses that type of technology. Then the next level up, aerated static pile with an embedded pipe, so basically pipes in a concrete pad, and a textile cover. So there are a range of textile covers, but the one, I suppose, most commonly understood in the New South Wales market is the Gore cover system. Concrete tunnel, fully enclosed forced aeration. There are a wide range of concrete tunnel, of that type of technology. It's a technology that's been around for years, out of the mushroom industry. It's the most infrastructure intensive of the selection we've got here. The composting systems we modelled have been generalised, and the actual costs for the various systems will of course depend on the individual situation, the individual supplier, and the market at the time. So there are generalisations definitely in this analysis. However, the same analysis could be, and we have actually applied it to specific sites, in specific situations. So open windrow, I think we're all generally familiar with it. What we modelled was not using a front-end loader for turning. It was using a purpose-designed turner, such as you see in this picture. In fact, I think exactly this turner as you see in this picture. And that is significant because obviously a purpose-designed turner costs a great deal more than just using a loader. And that is reflected in the small scale, the cost of the small scale modelling that we did. So for those of you who didn't see the pictures this morning, this is a pipe on ground system, aerated static pile, and you can't really tell because it just looks like more compost, but the model we used was modelling with a layer of 300 mil layer of finished screened material. So generally it's the 10 to 30 mil fraction that you layer on top, and it acts as a biofilter, and as described this morning, it is quite effective in filtering odour. Then you have a covered aerated static pile. We can't see it very clearly in this picture, but it's a concrete pad with a concrete backing wall, and it still has the aeration, basically the blower system going in underneath, but those blowers or those pipes are not sitting on top of the ground. They're in the concrete pad itself. And there are all sorts of ways to make sure that those channels that allow the air to come out into the pile are not clogged, although that's a great challenge for anybody operating those facilities. And the same thing with tunnels. So very much the same thing, except instead of having a flexible a textile cover, it's fully enclosed. You are in a concrete box. And you can see there the sort of, you can see it's much more, it's in a shed, it's entirely locked up, enclosed system. So yeah, there's obviously significant control of the air flow coming through that facility and of the odours that may or may not arise from the process. Okay, you're not meant to read this in detail, obviously, but this gives you an idea of the approach the complexity of the approach we went through. We took a modular approach. We standardised the processes that each technology was being, the way each technology was being implemented, so the process that the technology was using, to 8 weeks, 4 sets of 2 weeks, split into 4 phases of 2 weeks. We made provision both for storage and dispatch, and provision for managing the water and basically the environmental issues associated with each piece of infrastructure. To be closer to reality, we did minimise the amount of environmental controls that were put on the smaller facilities to reflect reality. Generally speaking, smaller facilities, less overall impact, less environmental, less infrastructure put in place to control environmental impacts. Okay. This is not, this costing model is not a facility design tool. We basically looked at a reasonable design configuration for each system, and that was really about how many modules or how many tunnels, how many batches of material would be run at each scale, which is reflected in the scenario design you see up there. And you can see that one thing to point out clearly, the first two systems are working with forced aeration, so the enclosed composting system runs across the first 3 phases. But with the tunnel system, what is common in the marketplace is that only the first phase goes in the tunnel, because it's just too expensive to have tunnels for the entire 8 weeks of the process. It's normally somewhere between 10 days and 3 weeks. So we've gone for 14 days here. Part of our assumptions is that there's a minimum of 2 modules required for stage 1, because you need to be loading one while the other one is operating, going through its first phase. We have assumed a 40% mass loss through the process and a 650 cubic metre batch size for each unit. So we're getting into a fair bit of technical detail here. All of the scenarios assume that the maturation phase occurs in an open windrow. So that's the 4th stage you see up there, and that's why there's 0 in each case. Okay, so what we did is converted all of the costs back to a $1 per tonne figure. And here are the more expensive ones, and as you can see very quickly, at a small scale, these become fairly prohibitively costly. And these are all low-end numbers. We've been as friendly as possible in our analysis of these more expensive technologies. The tunnel costing in particular is very conservative, because we're only allowing for that first stage of enclosure for the first 2 weeks, so only the pasteurisation phase, which, as I said, is very common in the marketplace. And the tunnel systems vary in cost significantly, very significantly, as a few in this room would know very well. And this model basically uses the lowest cost we could find. Some of the high-end European systems would be double the cost we modelled in this. Okay. So here is at the lower end of the scale, and you can see the numbers are significantly smaller. Now, using that rather expensive windrow turner for a 5,000 tonne facility obviously gave quite a high cost for a windrow composting with for a windrow composter for only doing 5,000 tonnes per year. But once you get to scale there, you can see windrow composting getting very cost effective, around the $50 a mark for $50 a tonne mark for a 30,000 tonne per year facility. Small scale windrow systems would generally use loader turning, which would bring those high-end costs down under $60. What have we got here? These ones here, they would come down more like that. This would come more down that level if you'd use a loader turning system. So the pipe on ground covered ASP is as you can see here, less than $60 an input tonne cost base, and is scalable. You see how in these you get a variation, it gets more, obviously the less tonnes you run through, whereas here the numbers are much more similar. There's not as big a variation. And that just reflects the scalability of that approach. So the key savings in that approach over the ones we saw in the previous slide is that there's a relatively low cost of the forced aeration equipment and the hard stand, much less concrete. You would think that the covering it with compost would cost you a great deal more in labour. It doesn't turn out that way when you do the analysis, nowhere near enough to compensate for the extra cost of the infrastructure. The other thing is that a compost covered system allows FOGO material to bypass the pre-grind and pre-sort step. So crucially, when you're receiving bin-based FOGO, it's contaminated, and you generally want to grind it first before you load it into either a covered pile or a tunnel to maximise the capacity of the system, because you paid money for that capacity, and you don't want it you don't want to overuse the volume. So the compost cover system allows you to basically stack the pile higher and avoid that pre-grind step. So you're only grinding and screening at the end of the process, not at the beginning. And there's a fair bit of detail to that, but you can come and ask me about that later. So some of the assumptions, that's the results. Critically in all of these analyses, the assumptions is where the rubber hits the road. Due to the food content of FOGO, we've assumed that it must be formed into a batch on the day it's received. Okay, that doesn't necessarily happen everywhere, but it is the practice that regulators will be expecting in the future, and you would not get away with doing it any other way, particularly in the extended regulated area of New South Wales, I'd suggest, particularly if you're a private operator. Textile cover and tunnel systems require a grinder on site, therefore, every day to allow the size reduction to occur and for each batch to be loaded straight away. Systems covered with finished compost can be loaded and covered without the pre-grind step, and the assumption is that stage 1 material stage 1 uses the stage 4 material as the cover material. Running through a few more of the assumptions there, I'll just pick out the most important ones. Yeah, I think I've covered most of that before. Critically, for the model, we've modelled it over a 10-year lifetime, so everything's amortised back. It's going to operate 52 weeks a year, 7 days a week, 8 hours a day. That's not necessarily applicable in all cases. There is a limit to how much food waste some of these systems can handle, so the assumption is that no more than 15% by weight of the material is food waste. And we're assuming we're not paying for water, essentially. Okay, so just finishing up, learnings. To emphasise, $60 a tonne for the compost-covered aerated static pile is a base cost. Overhead, product marketing and profit would add in the realm of $40, which probably brings you to a more familiar price in the marketplace. Critically with that unit, the point I made earlier, to reinforce that, scalability is important. Being able to do small-scale facilities in areas where you can't aggregate enough material is critical to their commercial success. Yes, more infrastructure, done well, critically, built well, well designed, well implemented, provides greater buffer for operator error, greater safety, and more process control in some cases. But more training, tighter management can bridge that gap for the more simple systems. And from the title of your presentation later today, Rob, you're also pushing simplification and simple options. And larger facilities can combine options. So maybe we put, for instance, tunnel systems, when we get to scale, tunnel systems on the front end, and then use some of the aerated static pile systems, the more simpler pipe-on-ground systems as stages 2, 3, and 4 to get the most cost-effective facility. Okay, perfect. Thank you.